Welcome to the Deep Dive. If you're here, you're likely tracking the latest in machine learning. And today, we've got something pretty interesting on knowledge graphs.
That's right. We're looking at a new paper proposing a unified way to build what they call generalized knowledge graphs, or GKG.
GKG, okay. And why is that unification important for someone interested in, say, advanced AI?
Well, think about it. Right now, we often build different kinds of knowledge bases separately. You've got your standard knowledge graphs, your event knowledge graphs, and your common sense ones. This paper tackles how to bring that all together. More efficient, potentially deeper insights.
Right, so the paper's approach is called GKG-LLM. Makes sense. Generalized knowledge graph construction using large language models.
Exactly, and those three types you mentioned, maybe we should quickly recap them.
Good idea. So KGs are like facts, right? Entities and relations. Einstein developed theory of relativity, that kind of thing.
Perfect. Then EKGs track events and how they link up, especially over time. Think WW1 started before Treaty of Versailles signed.
Gotcha. Events and sequences. And CKGs.
That's the everyday stuff, the implicit knowledge, like rain, causes, wet ground, things we just sort of know.
And the problem, as the paper points out, is that we usually build these using totally different methods.
Pretty much. Different techniques, different data sets, often in silos. It's, inefficient. You miss out on potential synergies between these different kinds of knowledge.
Makes sense. Why have three separate efforts if the goal is just knowledge?
That's the core question the authors are asking. They see the potential for, better resource use, maybe richer understanding if it's all integrated.
But it can't be easy, right?
Yeah.
Extracting a simple fact versus understanding event flows or common sense, they seem like quite different tasks.
Definitely a challenge. And that's the hurdle the paper claims to overcome, those task-specific differences. So our mission today is to unpack how GKG-LLM pulls this off and what it might mean for AI research.
Okay, let's dive in. How does GKG-LLM work fundamentally?
The key insight really is that all three graph types, KG, EKG, CKG, they share this basic structure, the triplet: subject, predicate, object.
Ah, okay. So entity, relation, entity in a KG.
An event, relation, event in an EKG, or maybe concept, relation, concept in a CKG. It's all triplets underneath. GKG-LLM really leans into that commonality.
And how does it use that commonality? What's the method?
They use a pretty clever three-stage curriculum learning approach. Think of it like teaching the model step by step. They start with a strong base LLM, one of the powerful foundation models we hear so much about.
Right. Makes sense to start there. What's stage one?
Stage one is KG empowerment. They basically feed the LLM lots of data from standard knowledge graph data sets. The goal is to give it that foundational skill and just spotting entities and basic relationships.
So learning the nouns and verbs of knowledge, kind of.
Yeah, that's a good way to put it. The model that comes out of this stage, they call it G-micro, and they use standard cross-entropy loss to train it, basically rewarding it for getting the facts right.
Okay, G-micro handles the basic facts. What's next?
Stage two is EKG enhancement. They take G-micro and start feeding it event knowledge graph data. This is about adding the ability to handle dynamics, time, sequence, causality between events.
Ah, so building on the facts to understand stories or processes.
Exactly. This boosts its ability to get temporal dependencies like before and after, and maybe some simple cause effect. This enhanced model is called GMID, still using cross-entropy loss.
Got it. KG basics, then EKG dynamics, stage three.
Stage three, CKG generalization. Here they bring in the common sense knowledge graph data sets to GMID, but they do something else interesting too.
Oh.
They add what they call counter-task data, specifically the WebNLG dataset.
WebNLG. Isn't that about generating text from structured data, like the opposite direction?
Precisely. The idea is to stop the model just getting good at extracting triplets. Making it generate text from structure forces it to, generalize better, understand the relationship more deeply, maybe avoid overfitting on just extraction.
That's quite clever.
Yeah.
So it's not just about pulling knowledge out, but also understanding how to express it.
Right. And this final model, after all three stages, is the GKG-LLM.
Okay, that framework sounds logical.
Yeah.
But you need data. Lots of it, I imagine. What did they use?
Oh, yeah. The data collection was a huge effort. They pulled together data for 15 different subtasks from 29 different data sets, covering KG, EKG, and CKG.
Wow. How much data are we talking?
It ended up being around 806,000 training samples and about 140,000 for testing, so quite substantial.
Can you give some examples of those subtasks? For KGs, maybe?
Sure. For KGs, things like relation extraction just within a sentence, but also across a whole document, which is harder. And even tasks where you have to find both the entities and their relationship at the same time.
Okay. And for EKGs, the event stuff?
It was things like identifying events in sentences, figuring out who did what to whom within an event across a document that's argument extraction, and crucially, getting the temporal links between events right.
And the common sense tasks, CKG.
Those were more about abstract stuff like generating summaries or figuring out logical connections between text snippets, natural language inference, that kind of thing.
And they categorize this data somehow. You mentioned testing.
Right. So you had the main in-sample data for training and testing, then the WebNLG counter-task data. And importantly, they had separate out-of-distribution or ODE datasets.
ODE? Stuff the model never saw during training at all.
Exactly. Datasets called TCR, causal-TB, R8. These were purely for testing how well the final GKG-LLM could generalize to totally new data it hadn't been trained on. A tough test.
Makes sense. And to make all this varied data work together, they needed a standard format.
They did. Everything got converted into a unified structure. An ID, an instruction telling the model what to do, a flag for few shot or zero shot.
Wait, few shot versus zero shot?
Yeah, so zero shot means just giving the instruction. Few shot means including a couple of examples of the task right in the prompt to help the model understand. They used a mix.
Oh, okay. And the format also included the input text and the expected output triplet.
Correct. And they even used GPT-4 to generate lots of different ways of phrasing the instructions for each task.
Why do that?
To make the model more robust, So it doesn't just learn to respond to one specific wording of a command, helps it generalize. And balancing few shot and zero shot examples also aims for better adaptability.
Okay, massive data set, unified format, clever prompting. But training these big models, it's expensive computationally. How'd they manage the fine-tuning?
Good question. They used a technique called LoRa plus AC. Stands for low rank adaptation. It's a parameter-efficient fine-tuning method.
Parameter-efficient meaning you don't have to tweak all the model's parameters.
Exactly. Instead of retraining the whole huge model, LoRa Plus cleverly modifies only a small subset of the parameters by adding these low-rank adaptation matrices. It's much, much cheaper computationally.
Like making small, targeted adjustments instead of rebuilding the whole engine.
That's a great analogy. And they even use different learning rates for different parts of these adapter matrices, allowing for finer control. Helps it learn efficiently.
All right, so we have the framework, the extensive data, the efficient training strategy. The million-dollar question, did it actually work? How were the results?
They were pretty compelling, actually. GKG-LLM showed significant improvements across the board in domain data, OD data, even the counter-task stuff. And that's compared to some heavy hitters.
Like what? Who were the baselines?
They compared it against big closed source models, GPT-4, Claude 3, Gemini 1.5, and also strong open source ones like Llama 2 and Llama 3, plus models fine-tuned specifically on single tasks or integrated data.
And GKG-LLM came out on top. Any specific numbers?
Yeah, for the KG tasks, it beat the closed source models by at least 12%, which is quite a jump. It even beat a model tuned only on KG data by over 7%.
Wow, okay, so even the big general models struggle with specific KG extraction compared to this focused approach. What about EKGs?
Similar story. Minimum 9.8% improvement over the closed source models there. Another approach, integrated SFT, did well on some EKG tasks, but GKG-LLM was consistently at or near the top. And critically, it really shone on the ODE event datasets, TCR, and causal TB. Better generalization.
That ODE performance seems really important. How about the common sense stuff, CKG? That sounds harder.
It generally got the best or second best scores there, too. GPT-4 did really well on one specific OD dataset, R8, but GKG-LLM was right behind it. And importantly, GKG-LLM aced the WebNLG counter task.
The text generation one.
Yeah, suggesting it's got strong capabilities not just in extracting structure, but potentially using it too. Overall, they reported an average gain of about 7.5% over the best baseline across all the different GKG tasks.
That's a solid average improvement. You mentioned the three-stage KEC training order. Did they confirm that order matters?
They did. They figured there's a sort of natural progression, basic facts, KG first, then how things unfold, EKG, then the more abstract common sense, CKG, that builds on everything.
Like learning levels.
Kind of. And they tested other orders, like starting with EKG, and found that, yeah, the KEC sequence gave the best results overall. You could actually see performance improving on tasks across the board as it went from G micro to G mid to the final GKG LLM. It generally beat models trained only on one type of data, too.
And what about those data tricks? The diverse instructions and the few-shot examples, did they prove they were necessary?
Yep, they ran ablation studies, basically, removing components to see the impact. Taking out instruction diversity hurt performance a bit,
Okay.
but taking out the few-shot examples, that caused a bigger drop. Seems giving the model those few examples to learn from was really beneficial.
And taking out both.
Biggest drop of all. So yeah, their data construction strategy with diverse instructions and few-shot learning really seems to pay off.
Let's circle back to the out-of-distribution performance. That seems like a key strength.
Absolutely. Remember, GKG-LLM never saw those TCR, causal TB, or R8 datasets during training, but it still managed the best overall score on them combined.
Better than the big commercial models.
Better than the second best model, which was Gemini 1.5 Pro by about 5.4%. That really speaks to its ability to generalize what it learned to new unseen situations.
Did they look at how much data they needed? Is more always better?
They tested that too, training with different percentages of the data, from 10% up to 100%. Performance generally went up with more data, as you'd expect, but the gains started to flatten out after about 80% of the data, diminishing returns. Suggests that with this setup, just piling on more and more data beyond that point might not help much more. You might hit a limit based on the model size or training approach.
Interesting. So there's a sweet spot, potentially?
Seems like it. And that trend was similar for KG, KG, and CKG tasks.
And finally, how does this fit into the broader research landscape? Did they position it relative to other work?
Yeah, they acknowledged prior work on specific tasks like relation extraction or event extraction, and obviously the huge progress in LLMs generally.
But their main claim is the unification.
Exactly. They stress that this study appears to be the first to really tackle the construction of all three generalized knowledge graph types, KG, EKG, CKG, within one single framework, specifically by fine-tuning these open source LLMs in that structured three-stage way. That unified approach is their key contribution.
So boiling it down, the big deal here is showing a practical, effective way to build more comprehensive knowledge graphs using LLMs, potentially breaking down those old silos between fact, event, and common sense knowledge.
I think that's a fair summary. It's a concrete step towards more integrated knowledge representation, leveraging LLMs through that specific curriculum learning and data strategy. The results, especially the generalization, look promising.
Okay, cool. That brings us nicely to our novel notions segment. Time to speculate a bit. Based on this GKG-LLM work, where could this lead? What's a potential next step or research idea?
Well, one idea that comes to mind is using something like GKG-LLM for dynamic knowledge graph upkeep. Imagine it constantly reading new text, news articles, scientific papers, whatever, and automatically identifying and integrating new facts, new events, new relationships into an existing graph, keeping it constantly up to date.
Like a self-maintaining knowledge base.
Exactly. In fields that change super fast, like research or news, that could be huge. Maybe you could even use reinforcement learning to teach it to judge the quality or relevance of the new info it finds, like automated fact-checking and integration at scale.
That's ambitious, but I can see the appeal. A knowledge graph that evolves on its own. Okay, I've got one too.
Go for it.
Since GKG-LLM learns connections across facts, events, and common sense, could we use it for prediction? Or maybe more complex inference?
How do you mean?
Like if it understands the typical sequence of events and the underlying common sense rules in a domain, could you prompt it to forecast what might happen next, given a current situation described to the graph?
Interesting. So using the learned structure for temporal or causal reasoning about the future.
Yeah. Maybe identifying likely future events or even hidden causal links based on the patterns it learned across KG, EKG, and CKG data.
Yeah.
It would need some clever prompting, probably.
For sure. Predictive modeling is always tricky, lots of uncertainty, but using this kind of rich, unified knowledge structure as the basis for forecasting, that's definitely a thought-provoking direction. Could be useful in economics, maybe healthcare.
Potentially, but as always.
Right, disclaimer time. These are just novel notions, speculative ideas to get you thinking, not guaranteed research paths or product announcements.
Absolutely. So wrapping up, the GKG-LLM paper presents a really solid step toward unifying how we build knowledge graphs. The three-stage framework, the data strategy, the results, is impressive work.
It definitely moves the needle on leveraging LLMs for structured knowledge in a more holistic way.
And if you want to get into all the technical details, the full paper is linked in the description for this deep dive.
It really makes you wonder what other areas of AI could benefit from breaking down traditional silos and finding these unified approaches. The potential seems pretty vast.
Indeed it does. Something to ponder. Thanks for joining us for this look at GKG-LLM. We'll catch you on the next deep dive.